I will talk today a bit about how we're using compound discover at Paul Scherrer Institute, and we are working in many different fields, so this is why the title is also more general. And I will just pick two examples how we actually kind of misuse compound discover, that is make for metabolomics, to actually look at the different fields, because in the end of the day we are all looking at the small molecules in this case, and then we can learn and transfer the knowledge between the domains and not really reinvent the wheel every time we are working with those components. Yeah. So this is Paul Scherrer Institute. As you can see, we have two sides. This is the west side, east side, and we belong to ETH domain together with ETH Zurich, ETH Lausanne, EAWAG, and all other institutes that are in the domain. And we are the largest one, having 2,200 employees. We are working in material and matter, energy and environment, and human health. And why PSI is kind of a really good place to work on it. We have many of the facilities in-house that people actually travel to us, and from Japan, from US. So we have here synchrotron, we have a neutron emission source, and we have a free electron laser in-house. And this is something that is really unique and enables us to do research on a completely different level, like it's done at universities, and we actually located here in the energy and environment part of the institute. This is a bit about my background, so why I'm working with small molecules. As you can see here, I'm biochemist by education. I have done biophysics, oxidative footprinting with proteins. So till Novartis, I was mostly working with large molecules and would actually better fit in the other session than in this one. And in the Novartis, I was working on peptides for biomarkers and somehow switched to small molecules. And then somewhere here on the time scale, Fukushima happened, and this was the point where I was really reconsidering what I'm going to do. And then Swiss government decided to have this energy strategy 2050, where we are going to go off the nuclear energy. And then at the moment I'm working on this strategy and helping to implement biomass as replication for the energy source. So more into details, and this is why I like to be here, and we are really talking about low to medium level stuff, and try to solve problems that we have on the daily basis. And this is how we actually work in the mass spectrometry with our mass spectrometers. So we do daily calibration of our MS. It's actually, everyone says this is not important, but I always find that the resolution is worth nothing without precision. So if you have high precision data, you actually can narrow down, speed up your processes, and getting, in most cases, only one good sum formula. And with this sum formula, your life gets much easier. So we weekly clean our LCMS. We are sometimes working with biofuels, and they are really like very dirty components. We do regular maintenance in-house and with a thermal service. We have standard methods. We actually use all 4 channels in our LC system. We have all 3 different sources that we also use. And at this point, I can really say this is not only marketing, but Accicure, RPMS. We have tried many different columns on the market, and we end up with this one, that being a general purpose RP column that is working the best, and it's almost undestroyable. So how we actually collect our data? We're running usually 3 times MS1, 1 time MS1 with the polarity switch, and then we go for 1 data-dependent MS, so MS2. Go to the compound discoverer, generate inclusion list, and inject the sample again with inclusion lists, or sometimes we have to split inclusion lists into 2 lists and run it several times. So what we are actually trying to get is, for all the components that we're interested in, MS2 spectra. And then if the beamer is responding, this is how we crunch our data. So we have a nice workstation with 56 cores, a bit of RAM, a 2 SSD, and what actually would be great if Compound Discoverer would be able to use GPU technology to actually speed up all the calculations. And then we have also 2 nice monitors to actually be able to pull all these dockable windows within Compound Discoverer and have really overview what we are working on. And this is kind of in-house tool that I programmed a couple of months ago, what we actually call sequence generator. So it's very easy to copy paste from your Excel list or whatever the PhD students, postdocs are doing. You copy your samples, you put your short name, project name, positions. You can choose between different instrument methods and how you are going to run your acquisition, and this really saves us already several hours of work of really tedious typing this into Excel list. And this is also generated the name so that you always know who has run the sample, which project it belongs to, and this is done in the way that you can directly import it to the Compound Discoverer, which again saves you a lot of time in putting study factors and all other stuff. And then you just press generate sequence, you get the file. So this slide was already seen today, so I'm not going to talk much more about it, but it's really one of the bases and fundamentals how we are actually assessing different levels of complexibility and trust in our data or trust in the identification that we have. On top of this, we have now a technician who is actually organic chemist by education, and we are starting also to synthesize components that we are trying to identify to get really this level 1 identifications. And this is how I started actually the whole presentation, and Guido certainly knows this slide, how I'm actually trying to build the workflow, and all these points here, they were empty at this time point. So now I'm really happy that we have several tools filled in, and that this is in great respect a really automated workflow how we can actually generate and identify our results. So what we are looking at PSI, I told you I'm in Energy and Environment department, and my primary goal is actually not depicted here. So what we have also analyzed the samples from the Antarctic region. This is the first time that the people actually get to the Antarctic part of the world and collect the first ice sample and air samples. This is really rather challenging. Then we have all the issues about the environmental impacts on humans. I'm still working in collaboration with the people from biology department, working mostly on quality control for the GPCRs, and our main goal is actually to produce something like this. This is biocrude produced from any type of biomass, and the ultimate goal is to actually produce the kerosene, because this is the only way of transportation that you will not be able to electrify or do any other things to actually allow the CO2 neutral transport in the aircrafts. And this is together with a consortium in the scope of the High Flex Fuel project, which is a Horizon 2020 project across the whole of the Europe, more or less. And this is the stuff that we're actually looking at, and then the products of it. And when I first time sent those samples to many vendors, including Thermo, they send it to me back and say, we are not ever going to look at those samples because they are so dirty. So we had a really difficult time to actually get them analyzed. And why all of this is important? So I'm now coming back, not only really looking at science, but also looking at political impacts and what we are doing, especially in the segment of climate change. Is the climate change true, yes or no? So many people in Europe would say yes, several people in the US would say yes, some other will say no, but actually scientific data doesn't really allow us at the moment to be 100% sure. And this is why we have so huge error bars on some of the measurements, that we cannot really say how big is the impact of the humans on the climate change. On the mean values, everything is clear. But if you really want to be scientifically on a safe side, you have to say on some aspects we don't know exactly what we are doing. At the moment, we don't have a precise methods. We don't have actually kind of standardized way to look at. And this is very important, not only from the scientific point of view, but also from the community point of view and global point of view. And this is why we are working on this. So, and I'm switching the topic, and this is, for a biochemist, probably the farthest way that you can go from biology, proteins, you go to catalysis. And here we have looked at the ruthenium catalyst on an active carbon. So on the active carbon, you can think what it is. Ruthenium is very expensive rare earth material, and this is the only catalyst that it's able to gasify biomass under supercritical conditions. So you want to keep this catalyst as long stable and in production as possible. So, and this is where if you talk with chemical engineers, they say, oh, what's happening with the cat? It's dying on sulfur, or there is some coke. And then you ask, what is coke? And they say, coke. It's like, whatever, it's coke. So this is actually what triggers my interest, and I wanted to see what coke is. So I extracted this catalyst, either fresh, that was never used, from the same batch, active, that was used but still fully active, and spent, that it's actually dead catalyst. And this was extracted using these organic solvents from very polar to totally apolar solvents, so you would be able to extract more or less everything. And this is just accepted a few weeks ago in ChemCat Chem, so you would be able to read it if you're interested in. And for the first time in my life, even as biochemist, I was using Volcano plots. And Volcano plots are really the way to distinguish data, especially if you have paired data. And this is really, if you want to see what is happening or what are the most important aspects of your on your sample, then this is really a great way to work with. And as you can see here, I was pretty strict, like putting the p-value of 0.01 and log 2 of like 2 or 3, and then having two groups of data. So the next was to actually look at Van Crevelen plots. What we're actually seeing there, in this case, it's H over C. So this is kind of normalization unit, that it's very useful not only for the in any case on the small molecules, because all these molecules that are lying on the same line are actually kind of homologous. So in this case, it's downregulated species. You see all of them are mostly blue, so it means they're all aliphatic. Orange would be aromatic, and red would be polyaromatic. And then if you see what's upregulated in the sample, so the right part of the Volcano plot, you see that the situation is changing dramatically. So on the spent catalyst, you have much more of the condensated and polycondensated species. And all these were run with AZ plus minus, APCI plus minus, and combined together. And then what I also like to do is kind of kernel density plots. So here we have a spent and the active against double bond equivalence. So you can clearly see on one side, double bond equivalence in the spent is much higher than in the active. And we have also shift in the molecular weight from somewhere around 200 up to 400. And there is something that evolutionary biologists actually have done in 70s, and most people have forgot this, and in 90s they rediscovered it. So you can actually plot mean oxidation state of the carbon in different parts of the cell, and actually see how they are optimizing toward the function or optimizing toward the within the kingdom. And we can also see that there is a difference, but I don't have yet explanation for it. So let's hope that in the next works we could actually get more deeply into the structural elucidation on these components. And then the key question is, could we keep the catalyst still active after we wash it? For this we have performed the experiments, batch experiments on the activity of the catalyst, and you see that the catalyst, after you have extracted the active catalyst, you get the full functionality back in the production of methane. But the catalyst that it's already dead, you can partially recover it, but you can never get back to the full activity, which means you have to wash your catalyst before it actually dies completely. And then I'm switching again the topic to totally different sphere, and what I'm actually very keen in looking at is the lignin. The lignin is actually the second most abundant polymer on the earth. So first is cellulose, then we have a lignin, and lignin contains the most energy saved in a molecule. And this is the only sustainable source of aromatics. At the moment, lignin is just used in a most primitive way via burning it. So we could actually, this is how it's used. But as you see how it's built up in the plants of different aromatic alcohols, which are branched, and actually you have kind of 3D structure, and this is what's preventing, what is giving the trees the possibility to stand up, which is what is giving the trees the possibility to transport the water from the roots to the leaves. This is lignin. And once you extract it to actually produce paper and pulp, there it's usually used as fuel to burn the whole, to burn it to get the heat for the whole process. So lignin you can think as proto-lignin, which is kind of native-like, and technical lignins, which are extracted, and by extraction you have to modify it. Otherwise you cannot extract it. They are covalently linked to cellulose and hemicellulose. So what we are actually aiming for are compounds like this, so that you have functionized aromatic units that you can use as building blocks or as platform molecules for the chemical industry, for the pharma industry, pesticides, and so on and so on. And one of the key points where people are actually looking at is the vanillin. Research on extracting vanillin from lignin is more than 130 years old. There is more publication on this than probably on any other part of the science. So the people have tried many different things, mostly in the approach cook and look. I'm trying this, I'm trying that, and then see how much vanillin we get in the end of the day. So we have there a bit different approach. What we are actually using is biphasic system. In this case, it's a water octanol biphasic system. Lignin is not soluble in any of those. And then we are actually trying to kind of chop the lignin apart in the water phase, and as all these aromatics are more soluble, like 10 to 20 times more soluble in octanol, to extract them to octanol phase and protect them from further degradation. And this is how it actually looks like. So in this condition, what I was doing is like only focusing on vanillin and see if actually our production of vanillin is the bottleneck or is something happening to vanillin. So if you have vanillin and you heat it up in the microwave, you saturate with oxygen as oxidizer, you use octanol water, in this case in acidic environment, you see that the vanillin is actually degrading. So after 40 minutes, you have like 25% of the vanillin is gone, or this corresponds to the half-time of degradation of 17 minutes. And you see here before and after, this is the octanol phase up, and down is water, and after you see that it's colored. So this color means something is happening, but we don't really know how much is happening and what is happening. And this is where I was very excited when Compound Discoverer 3.0 came out. because I then could actively use it. So on the first assumption, you would say we have vanillin, we get a vanillin derivative, and this is why we actually losing our vanillin from the solution. But in theory, it can be a secondary derivative, third derivative, or you can actually have a secondary derivatives from one of the derivatives that could actually react together. So it's actually like if you don't like math and statistics, it's the way to stop and run away. But yeah, this is set of parameters that I actually used. Vanillin at 3 different concentrations, 3 different temperatures. We have oxygen as oxidizer and argon like a blank. So you have 1 parameter less, and then different time points. And many of you know what -1 means. This is for energy community very difficult to explain that you use -1. This is sample that nothing is happening to it. And 1 is you mix everything together, putting in microwave, take it out. And it might already cause some changes. And then stable labels. So you are actually able to buy vanillin 13C labeled for, yeah, 1 Swiss francs per milligram, which is not really very expensive because we don't really need many of those. And this is the workflow that I was using for the rest of the data that I'm going to present. So we have input files, select spectra, very classical way. And something is missing here. Analyze labeled components. And this is now coming in the Compound Discoverer 3.0. And I found this very interesting because in this particular case, vanillin is having 8 carbons. It's C8 component, and octanol obviously also C8 component. So the way how to distinguish what components you can get from the octanol conversion, or if the octanol is stable, and what you're getting from the vanillin is actually very easy to get if you have stable labeled components. And this is kind of filtering unit, how you get there. And here I would actually like to have kind of possibility to pre-select the default values. So every time I choose some of these filters that I have the values I use the most, and not the default values. And these are, I will now show you a couple of examples what can happen, or how I'm able to make at least tentative identification, or in one case even buying the standard and confirm what we are getting. So here it's actually the data from the Compound Discoverer at different time points. You see at -1 you don't have actually anything down there. Then at 0, this is just 1 short heat in the microwave. It takes like a minute, cool down. You see something is happening. At 10 and 40 minutes, you have a huge increase in the peak area. And from this, you have 2 isomers, which are in this case really nicely separated from each other. From the literature, they actually tell that vanillin, this is a dimer of vanillin, is the most dominant, or what should be actually happening with vanillin under those conditions. But you can see that this is actually not really true, because we couldn't really explain majority of the MS2 peaks. On the other side, you have these nice molecules that reassemble the vanillin, and for these ones, they have all 12 exchange carbons. So you know that you have 2 intact benzene rings in your molecule. And then you apply the fish scoring, and you get like top 3 candidates. And actually, in this case, is the second one, because this is commercially available. You can inject it, and you get exactly this peak. Then we have this other isomer, and this is like a side project, much lower abundant. And indeed, this is what was proposed in the literature. So what was identified, even in this case with NMR, was actually most probably not, it's actually not true, because we have standard molecule that we inject and the very same method, very same conditions, and you can see that you have two different distinguished molecules. And this is where compound discovery is really with this capability to have stable isotopes. So now my presentation is now stuck. Yeah. The other component that I would like to show you is this chemical formula at 3.08 minutes. So this is the peak here. It's also produced during the reaction. And actually, we haven't got any hit for this peak in either in compound discoverer nor in the ChemSpider. So this is a bit other approach. For this component, we also know that we have 6 labeled carbons. This is out of the filter. So this is best MZ logic match that we get. You can see, you can explain 2 formulas very nice. But the third one is not explainable by this component. Then you look at the MZ cloud, no match, but one similarity match. And it's actually vanillin. And this explains your missing peak here. And then you do a bit try around with combining the 2 structures and explain the whole formula. And this is the formula that would explain the whole MS2 spectra. So now, out of like 800 possible molecules with this sum formula from ChemSpider, you end up in one very good candidate that we are going to order and test if it's the true one or not. And then, what most people actually say, if you have vanillin and you have oxidative conditions, you will produce vanillic acid. And it is stated in almost all papers that you will find on this topic. And we can clearly say that this is not present. Even if you have some formulas for the vanillic acid, and you get running GCMS, you get NIST identification for this one. If you run stable label isotopes, you see that this is not coming from vanillin, that it's something else. So on one side, what I can tell at this moment is that we have a degradation products, and on the other side we have condensation products. And all the details I'm not allowed to tell you at this moment because we are preparing a manuscript, and yeah. And so now the only thing that I have done between yesterday and today is actually my wish list get one slide less long, because I was excluding most of the things that actually other speakers have put here. So what I'm doing is really this kind of old school. I'm looking to every and each peak in my identification. And unfortunately enough, even for high abundant peaks, you don't really have nice integration. Or if you run triplicates 2 times, it's integrated properly, and the 3rd time the algorithms decide to do something else. Then we have also cases where we have isomers that are not completely separated. And this is probably the most difficult case also for any algorithm to actually be able to find all the peaks, and then small changes in the settings of the algorithm might shift the identification. And for some of these isomers, I think that you are not at first moment very interested in. It would be great to be able to actually manually say, I'm going to take them all together, and give the user the possibility to actually decide in the end. Because if your peak integration is not right, all other tools in compound discovery are more or less useless, and all the analysis that you're doing afterwards is more or less useless. This is why I'm actually excluding those, and then running really like targeted analysis with Excalibur, and then in the end combining those data. And this is really tedious work that should be somehow avoided. Then we have also sometimes in source fragmentation, especially octanol or some higher alcohols. They tend really to have nice in source fragmentation, and actually some of them we really saw only in AZ or mostly in AZ, and then you see, okay, I'm looking at hydrocarbon in AZ, how it can happen, and then looking at retention time, you see that it's actually a product of the fragmentation of your parent molecules. Then we are doing most of our work with solvents that are volatile, like methanol. So we do everything on the balance, and it would be great to have kind of normalization already in the compound discovery to say this sample is 1.1 time more concentrated than the other, which would also change your peak areas and all the rest of the calculation. The structural editor, as you have seen, you have to do a lot, and it's really not the nicest to use. So what we are doing at the moment, we open ChemDraw and then copy paste the structures. So in the structural editor in compound discovery, you are not even able to put the cursor on the atom that you want to change and then say, okay, it's not carbon, it's oxygen, or it's sulfur. You have every time to do 3 clicks to actually exchange something, and this should be better. Then labeled, unlabeled, having them in mirror plot would also help to actually identify. For the labeled components, it would be also great to make a group and then also CV so that you can actually filter out. And if you have many molecules, then to actually be able to filter out everything that you find labeled in unlabeled samples. Filtering, as I told before, it would be great that we have in the options to have parameters for every and each option that you could adjust and save according to either your project or your preferences or whatever, because this is very very time consuming, and if you have to send for 20 groups always the same parameter, it's kind of difficult. And also to duplicate, if you have already a parameter, to duplicate it and just change the group that you're looking at. And I think 21st century GPUs are coming. Many people are doing gaming, which is great for scientific community because we get all these great developments in the graphic card actually to use for our research. And then a couple of acknowledgements to my boss. These are the people working with me closely on the mass spectrometry. We have also meanwhile acquired quite some funding, either from the EU projects or from Marie Curie, or we have also this BioSuite project, which is funded by Swiss government and Swiss National Science. And of course, all of you for your attention.